With the introduction of AI, training, distributed inference, it's just the need for bandwidth has skyrocketed.
Hasan, welcome. So great to have you here.
Thank you very much, Nick. Great to be here.
Great, thanks. And thanks for helping us geek out in the morning. You know, that was a great keynote. And actually, I really enjoyed it because it's like the whole Ethernet space has, not only evolved, but it's accelerated at a pace that we haven't seen before. And, we started off with 10 megabits back in 1983. And it wasn't until 2010 that we hit 100 gig. And like in the last 14 years, we essentially have gone from gigabits to terabits. So like right now, you're shipping like the chips with 800 gig, on them. And then you're now, and actually like significant like density as well on 800 gigs. And then you also have, obviously in the planning, 1.6 and 3.2 terabits. So let's first start talking about maybe that journey, around Ethernet, like that's been in our industry for like 3 decades, or so. And how it's now accelerated really thanks to like kind of the hyperscalers and also the public AI companies as well.
Yeah, Nick. Thank you for having us here. And you're absolutely right, right? If you go back just to the data centers 4 or 5 years ago, you would think like 800 gig, when is it going to happen? 1.6 terabit, it's going to happen, when it's going to happen. And if you look at the enterprise data centers, most of them even today are deploying like 25 gig, 50 gig NICs.
Yeah.
Right? That is the connectivity that you have. But with the introduction of AI, training, distributed inference, it's just the need for bandwidth has skyrocketed.
Yeah.
And the need for bandwidth is there is this use case, which is the backend use case. That's where it started off, which we call the scale out. And you can see the NIC speeds there with the GPUs are 400 gig and 800 gig today, and moving to 1.6 terabit. The Tomahawk 6 that we talked about this morning is actually supports 1.6 terabit ports, and it's shipping and it's in production. But even more mind-boggling is what is happening on the scale-up domain, right?
Yeah.
Scale up is where these GPUs are directly accessing each other's memory.
Yeah.
And, they have enormous amount of memory. We are talking about 40 terabits of memory bandwidth, 40 terabits of memory bandwidth today, moving to 100 terabits in the next generation GPUs. So you're talking about around 10 terabits of networking bandwidth that is required, 25 terabits tomorrow, right?
Wow.
And so it's just it's everything is accelerating at an extremely fast pace. This is driving some of the roadmaps on the Ethernet side. Right, we just released the 100 terabit switch, and 200 terabit, 400 terabit. We're working on it. Right, they're around the corner as we move forward.
Yeah, those are amazing numbers. So like I think I want to like have this conversation around the high end. But then I want to kind of relate it back to the large enterprise marketplace, because we're talking about kind of the scale of scale, like, the highest end of the marketplace. So in that, so networking is really different, at 800 gig, in the terabit range. So it's not just about connectivity anymore, but really it's a fabric that's really kind of connecting GPU memories together. And so we have compute and memory so locked into the network where there's synchronization, load balancing, the ability to kind of like support these really high burst rates, and these really kind of different traffic patterns. So maybe let's describe a little bit, or you can describe a little bit about like how networking and the function of networking has changed as we're into like this kind of realm or this scale now.
Yeah. So the role of networking, and if you really want to just talk about this, I think the scale and where networking comes into play is the use case in the space, right?
Mm-hmm.
And there is a use case for what we call scale up, right? This is where you want to connect most of these GPUs directly, accessing, just like you said, the memories directly. And in that particular space, actually bandwidth, like I just described, is extremely, extremely important.
Mm.
But the network, if you think about it, is actually simpler, right? Because what you want is you want these GPUs to be connected just one hop away.
Yeah.
Because that's how you get the best performance, right, for the models if you're doing training or you're doing inference. And so the key thing over here is the address space that you need is not very large.
Mm-hmm.
You do not need very, very large Ethernet headers. So this is where this concept of optimized headers has come into play. Right? There's discussion around Ultra Ethernet Consortium on this. And so you can optimize the header so the address space is small and you're not burdening, right, the fabric.
Yeah.
The other thing that's very important in this space is what I call reliability, right? Because these are memory transactions,
Yeah.
right? And it's extremely important that reliability is of extremely high importance in this case. But as you now start to scale out and you're talking about large distributed inference or training, the requirements are slightly different. Because, like you said, the AI workload is fundamentally very different.
Yeah.
It's the traditional network that we have, the data center that we have the TCP/IP traffic. It load balances itself very effectively
Right.
across different paths. In the case of AI, you have what we call elephant flows.
Yeah.
These are very large flows, very few of them. Think of this as an 8-lane highway. If everybody is driving in one lane, you're going to have congestion.
Yeah.
So how do you solve this load balancing problem? How do you solve the congestion problem? And the other very important problem is how do you recover very fast from link failures?
Yeah.
Because link flaps are a huge, huge deal, whether it's in any network.
Yeah.
Right? And if you have a link flap, which do happen, what you're going to have is, if you're doing training, you're going to go back to a checkpointed state, start the job over, your job completion time is going to be higher. So these are some of the problems that need to be addressed. The third problem that networking has to address is a lot of these data centers, the power is a problem.
Yeah.
Right? At some point of time, you're going to run out of power, you're going to run out of capacity. And if you want to extend these clusters across data centers, how do you do that?
Yeah.
Right? How do you keep this fabric lossless? How do you ensure that you have security, because now you're going outside your data center? And also, how do you go very long distances without compromising, right, on the performance?
Yeah. You
So
do
those
have
are
the
all
speed
things.
of light problem, there. But yeah, no, continue. Yeah.
Yeah. No. So those are the three different use cases, like you asked about, and those are the use cases that the industry is trying to address, right? And different requirements. But the good thing is, all of this can be done over Ethernet, right?
Yeah.
This is only one technology that, if you're trying to do the scale up, scale out, or scale across, that allows you to do this end to end.
Yeah. No, I'm with you on there. And obviously there's InfiniBand, and that's been like, serving really well in these large environments, as well. But there's a much larger community around the Ethernet space, and there's a large culture of innovation there as well. And to be able to kind of grow it as fast as the market really needs it. And I think also what's occurred is as these speeds increase, and as these chips that you have like right in front of us, are getting developed, the optics market has just exploded, just gone crazy. I guess maybe where's your thinking around where the EO conversion kind of happens, right? It used to be kind of in the modules, that you're plugging in, but it's getting closer and closer now actually into the interface on the chips. So can we speak a little bit about, or talk a little bit about, how kind of electron to optics and optics to, or photons and photons to electronics, occur? Where?
No, very good question. And absolutely, you really can't talk about networking without optics today, right? They are now just tied at the hip, right? These conversations have to happen together. And kind of like, I'll again go back to the use cases that I talked about, right? Because the optics requirements are evolving in all of these different use cases. Let's start with scale up once again. Scale up is really confined to a rack today.
Right.
This is where all of the XPUs or GPUs are connected in a rack. And dominantly, they are connected over copper. I mean, copper has been fantastic, right?
Yeah.
It has low power, it's cheap,
Yeah.
and it is very, very reliable. But what is happening is, to get the best performance for inference or for training, people want to increase this domain size. You want to go to domain sizes which are more than 100, because right now you're confined to a less than 100 today.
Yeah.
256, 512, maybe 1,000 in the next 2 to 3 years.
Yeah.
But if you want to do that, you don't have the reach with copper at some point of time,
Yeah.
right? Because there is the SerDes 100 gig, 200 gig, 400 gig. As the SerDes speeds increases, the reach for copper is going to go be doing that.
Yeah, the distance shrinks.
So the question really is how you solve this problem. And this is where we work together with the industry, right? With Meta, with Microsoft, with OpenAI, with NVIDIA and AMD, and release this MSA called the OCI MSA. Right?
OCI.
And this is really an open, interoperable physical layer specification for optical scale-up.
Mhm.
So essentially, the OCI technology will give you a reach of up to 2 kilometers, but without compromising on the benefits that you have with copper, right? Which is power,
Yeah.
which is cost, and which is reliability.
Yeah, and 2
right?
kilometers is big enough for a data center. That's
Big enough for these scale-up domains, absolutely. Right? As we look over the next 3 to 5 years. Now, you talked about photonics, right? That's the on the scale-out side of things. What's happening is, we talked about this Tomahawk-based system, right? 128 ports of 800 gig or 64 ports of 1.6 terabits. And this is going to go to 200 and 400. The systems are becoming increasingly complex. It's very, very difficult to cool. The thermals are a challenge.
Yeah.
So that's where the optics come in, the importance of optics come in. And, we have been investing at Broadcom for the last 5 years in this concept of co-package optics. We are on a 3rd generation. We released this thing called Tomahawk 6 Davison. It's the 100 terabit Tomahawk 6, but it also has 100 terabits worth of optical engines in there. The lasers will be outside, but
outside of the chip.
Outside, right? They'll be on the front panel.
Yep.
So, but the question really is the power benefits. I think they are well understood in the industry, right? There are others who are working on CPO solutions. You get 70% power savings when you go to CPO. But the big question has always been around reliability.
Yeah.
Because it's a big risk. Now you're integrating optical engines onto the silicon itself.
Yeah.
What if failure happens, right? Are you going to replace the entire switch?
Yeah, right. Yeah.
And this is where we have worked with a lot of partners on doing very extensive testing. Meta has been on the forefront of this. And they did this testing for co-package optics with us. And they were able to get these 1 million link flap-free device hours. And so the link flaps are that important.
Yeah. Well, because you have a link flap and then you're restarting that job.
Exactly.
From the very beginning. Yeah. So so go ahead, continue.
And similarly, now they're able to get up to 50 million link flap-free device hours.
Okay.
So you're getting reliability, which is almost 10x of what you can get with pluggable optics, right? So co-package optics is absolutely something that is starting to happen in the industry, and it's becoming the need. But, there are other initiatives out there, right? Arista came up with this concept of XPO, right?
Yeah.
Where you can actually have different optical choices, and you can, in a 200 terabit, you can fit in 1 RU. So I think what you'll probably see is a lot of work happening in conjunction between what's happening in network and optics, a lot of this integration.
Yeah.
And a lot of customers will not want to have a networking discussion without an optics discussion.
Yeah, I think so. Hey, so can we take a look at the chipsets that you brought?
Absolutely.
Okay.
Absolutely. So I think I brought a few things with me, right? This is the what we call the Tomahawk Ultra, right? I mean, 4 years ago, you talked about InfiniBand, and InfiniBand does a very good job in terms of low latency. Like for Ethernet, it was like one of the problems or one of the key things that we wanted to solve was how do you get very low latency at very high throughput? And this is what they solved. It gives you 51.2 terabits of performance at 250 nanosecond latency, 77 billion packets per second of performance. Great for scale up. And this is the Tomahawk 6, right? This is the only 100 terabit switch out there in the industry, right? That's there in production. Um,
So
and
how
in-
many ports of 100 terabit is this
so
support?
you can actually get 128 ports of 800 gig or 64 ports of 1.6 terabit.
Ah,
And I think on the show floor, you can see like some of the vendors already have systems, right, which are built with Tomahawk 6. This is actually running in production today,
Oh.
right? And shipping in production volume. Um, and you can actually build a 128,000 XPU cluster in a two-tier topology with this.
so which OEMs kind of use that chipset?
So what you'll find, Nick, is we will have our, for enterprises, a lot of customers use Arista, right, from us, Juniper, Nokia, all of them will have Tomahawk 6-based systems.
Okay.
And there is an ODM ecosystem, you saw like, for example, Celestica, EdgeCore,
Yeah.
Micus networks, and all of them have systems, right, based on Tomahawk 6s that are
Okay.
available today, right? So there's a very large ecosystem that is building on top of it.
Yeah.
And then lastly, but not lastly, but this is the Jericho 4, or a variation of this that we call Qumran 4D, right? You can see this is high bandwidth memory on here. And the reason why we have this high bandwidth memory is because when you're scaling across and you're going very long distances, you need deep buffers.
Oh, so that's the buffer allocation there.
So this is like essentially a 51.2 terabit router. You can get 64 ports of 800 gig in a 2RU form factor.
How many ports of 800 gig?
64 ports.
64
It's
ports.
it's a complete router with very large routing tables, with deep buffers, gives you line rate encryption, right? IPsec or MACsec. And you can go with ZR optics distances which are 100 kilometers or above,
Wow.
right, with this.
Yeah.
And so this small guy over here, right? This is what we call the Thor Ultra, right? This is the world's first 800 gig NIC. And we talked about, the NICs in, moving to 800 gig and 400 gig. So this is the 800 gig NIC. It gives you 800 gig of performance, but it also has capabilities which are there, which were discussed in Ultra Ethernet Consortium to modernize RDMA as a protocol, right? To support multipathing, out-of-order data placement, selective retransmit, modern congestion control. And this will be shipping in production in July of this year.
Okay, awesome. So like if I'm looking at like these chips here, so the optics then would be connected kind of like out this part, basically all around the chipset, right? So you're not bringing the optics into the chip. It's really on the board, and that's where the LEDs and the receivers are as well. Right?
Correct, right?
Yeah.
There are two ways, right? When co-package optics, actually, you can actually integrate the optics onto this Tomahawk 6, right? There will be a different package that you have.
So what do you mean when it'll be integrated right onto it, like on the chip?
Yeah, so they will be on the sides here, right?
Yeah.
But the lasers, like I said before, are going to be outside, right? They will, when you're building the systems, the lasers are going to be on the front panel, because lasers are one thing that probably have a higher probability of failure, and they remain outside.
Really? Okay, I didn't know that. So the lasers actually have a higher probability of failure than the silicon.
Correct.
Wow. Yeah. Wow. Okay. Go figure that. Yeah. And everything I'm assuming is mostly single mode fiber that's kind of connecting, into these systems so that I can get the data rates up that high.
Correct, right? It depends on, again, the use case. You have DR4, DR8, people are using FR, as you go with long distances, you're using ZR kind of optics.
Yeah.
So, and when you're just connecting scale up, it's copper, but some people will use AEC, right? So it just depends on the reach that you're looking for.
Yeah.
Right. And, you have different flavors that are available with these.
Okay. All right. So a little Overton window expansion question here. If this stuff was going to be on like an AI data center in space, how will we connect those GPUs?
Well, it's going to be...
Are those going to be direct laser to laser through, vacuum of space, or is that actually going to be switches?
Well, if you're building this data center connectivity, the question is the connectivity, you'll have these racks. So you will have this scale up domains and probably the scale out domains.
Same thing, huh?
Same thing, right? That's how you'll have achieve the connectivity.
Yeah.
Now the space and Earth, how does it work? I think there are some things that need to be figured out.
Yeah, that's right. Yeah, yeah. Well, yeah, getting all that data from space back down. Yeah, and okay, all right, awesome. Well, this is like really, really great. Thanks so much for bringing the props. You know, one, I love looking at hardware. You know, too, and those are like super impressive. So, all right, so now I want to kind of like lead us a little bit into like the enterprise marketplace. So obviously, most of the action for AI has been hyperscalers and OpenAI and Anthropic. Well, Anthropic has been kind of renting, compute, but Meta and others. So Tom Gillis had a really good kind of presentation too, right before yours. And he was talking about how both the ecosystem of like the enterprise marketplace is starting to work on smaller, more compact AI stacks for the large enterprise. So much more power efficient, not as dense around the GPUs around need. So how do you fit into that market segment, as well? Or are you working with like the other OEMs on how do we now package or repackage this technology so it's more accessible and affordable for large enterprise?
So Nick, I think the way that we build this is we have these small building blocks.
Yep.
Right. And just depending on the scale that you want to achieve, you can scale accordingly. Right. You're absolutely right. For the enterprise, you probably don't need cluster sizes, most of them probably don't need cluster sizes, which are 100,000 XPUs.
Yeah, for sure. Yeah.
But what you probably need is maybe a few hundred, maybe just a few. But even these products, right? You're not now talking about if you're using a Tomahawk 5 or a Tomahawk 6, you don't need hundreds or thousands of these switches. A single switch actually can support your entire domain, right? As we talked about, you can get 128 ports of 800 gig. If you use a Tomahawk 5, you can get 128 ports of 400 gig.
Yeah.
So your entire fabric could be a single switch. So this is what we have been able to do, that, these systems, they used to be 14, 16 RU, right? They consume 20,000 watts of power and they cost $1 million. And something like this, like a Tomahawk 6, is now shrunk it down to 2 RU, 1/7 the form factor. It gives you 8 times the performance. It is 1/10 the power, and it is less than 1/10 the cost.
Yeah.
So it's really
congratulations on those metrics. That's an impressive set of metrics.
Absolutely. There are enterprises who are doing this today, and for them, the entire fabric could be a couple of switches as they start off. And as the requirements grow, you can continue to scale out and grow bigger, right, with these form factors.
Yeah. Awesome.
Yeah.
Hasan, thank you so very much. It's always such a pleasure to have you and actually just kind of get into your world, and to see what you've been kind of building and working on over at Broadcom, because you are the engine that kind of drives a lot of the products that we see out in the marketplace. So thanks for coming on.
No, thank you for having me on the show, and congratulations, right? I see the show continues to grow. Yeah. And I think the next few years, this AI revolution is going to be hitting the enterprise even bigger. Yeah. And we look forward to working with you moving forward.
Awesome. Great. Thanks, Hasan.
Thank you.
Thank you. Thanks, everyone.